So now we're recording. This is where we left off last time. So we were talking about T carriers, basically about different ways of providing a WAN using it from the point of view of the telecoms carrier, right? So the telephone carrier is producing all of this equipment in here, all these switches, etc., for us to have our WAN connections. And yeah, the T carriers, particularly important from a point of view of telecom carriers, because they actually are very well understood and recognized and used packages that are sort of put together. It's just like you will have so much bandwidth over so much this month, and you get charged for what you use, basically. So yeah, there's T1. Now, the number of channels for these, that's kind of important. So you might need to do a bit of reference on that, but T1's got like 24, and then T3's got 24 times 28. Yeah. And so we have these devices, that basically the smart jack. It's also important to sort of have a look at that. We actually have to have some of our own equipment here. So we've got the CSU, DSU, which is basically, that's done by your router and your modem together. They make that. But then there's a smart jack, which is going to be provided by the your telco company. And then so that's going to be at your DMARC. Okay. So we were up to 29. LAN through a router with on a T1 connection. So the T1 connection, as we say, that's a bundle that's given to us by our telephone company, and they're going to provide us with this smart jack connection. And we've got our multiplexer, as it says there, router, and you could consider that also a modem. And then we are splitting that traffic into the different needs that we have in our organization. That's where we left off. So let's continue on. SONET, the important thing there in the name, it's given pretty clearly. It's going to be optical, so that's going to be optical fiber. It's using light instead of using electrical. So it's that gives it the high bandwidth. I mean, I hope you know by now that using optical, the reason why we use fiber is because it does give us a better bandwidth, and also further we can take that traffic further. So now it talks about interoperability. You can use multiple different protocols on it, on your SONET. It has fast transfer rates, as it says. Self-healing. Now we use this term SONET. It's only actually used in North America. So in the United States and Canada. The same or similar technology is used around the world, and we just have a different name for it. We call it synchronous digital hierarchy, basically everywhere else. So you might go somewhere else and say, oh, that kind of looks like SONET, but it's not. We're using a different name. It's basically the same. And so that's what we meant about interoperability. So SONET can be used across many different networks of many different companies. So they'll accept input from different network types, as it says, and then it'll format the data in so SONET's got its own frame. So it's kind of like it's kind of wrapping the packets that are coming from the other networks into its own kind of frame, and then it's able to, as it says there, multiplex those. That sort of combine things so that they're more efficiently transferring over the network, and then uncombine them afterwards. So that's what we're doing with a multiplexer. Demultiplexer is the uncombining, if you like, separate them out at the other end. So yeah, so this is what we mean by that. We've got a particular bit of traffic that we want to get from some host over here to some host over there. And that's going to be put through the multiplexer and sort of packaged in together with a bunch of other traffic from other places. And then that is all going to go across the transmission together. And at the other end, using algorithms, it's because your multiplexer is just basically a big computer. It's a network computer. Then they're going to split that out and send it on to the places where it's supposed to go. Yeah, so what it mentions here is quite important. The sonnet, how that works so well for them is everything is done by timing. And so if you've got a stream of data that has some gaps in it, what sonnet will do is it'll actually send along empty packets so that the actual timing is not ever messed up by pauses in the data. So the pauses in the data are filled up with sort of like empty packets. So they'll send without data rather than disrupt the schedule. So it's the timing that's important, that we get that message according to the timing that's sort of sent, indicated on the multiplexer as it sends. And so that's what, so the frames are a consistent size, and that makes it work. So if you can imagine, if each frame is the same size and each frame has a certain time, then that makes the calculations on the multiplexer of how we put it all together and how we pull it all apart, that makes that kind of work. Now we've got these optical carrier levels. They are used. They represent the speed of the data that's going to be passed on your sonnet. It's important that you sort of you learn those, and I don't see it mentioned here, but you should look and find out about OC3, and I think it's OC63. So you know the difference between layer 1 and layer 2. Layer 1, we're just talking about the physical. So that's in sonnet that would be talking about fiber. Layer 2, we're talking about the protocols that we use at the LLC, etc. And as it says there, some layer 2 technology are used. Now the good thing about layer 2 technologies is that if your WAN is based on layer 2 technologies, that can actually work over multiple kinds of physical technology. So you can combine copper and fiber together, and you'll say that I'm using frame relay. Now, having said that, yeah, in order to get the bandwidth right, you may be required to use some optical for that. So we have frame relay, ATM, asynchronous transfer mode, and multi-protocol label switching, which basically just means that we're going to use maybe a little bit of frame relay, maybe a little bit of ATM, maybe a little bit of something else. So that's what we mean by that. So what about frame relay? It includes ISDN, or no, sorry, it replaced ISDN. ISDN was a big thing in the 1990s. When I first got internet in the Middle East, we had ISDN. I don't think we had, into the early 2000s. And yeah, been replaced by that. So ISDN is giving us a better service with a higher bandwidth. So you have this concept of a data link connection identifier that, as it says there, which circuit to use for the frame. So that means that your frame is going to have the identifier on it to determine which circuit it will go on. So here's a diagram which sort of represents that frame. So we have special switches there that are provided by the ISP, your network provider. They're providing these switches. For us, sitting in this office, trying to communicate with these people in this branch office, to us, it seems like we've got a direct communication between there and there. So we're referring to that as a logical PVC. So it's a logical permanent virtual connection. So it's like as if we had a cable between us from the point of view of what we're doing. But in fact, what's happening sort of, and we don't have to worry about this, the telephone company is doing this for us. They have these switches that are actually taking that data and they're pushing it through their network. The fact that there's a cloud there means that there could be many other devices in there, right? You know, and network through there, but they will make sure that it gets to here. To us, it seems like it's just direct between there and there. So to us in this network here, it just seems like we've got two lines, one going to this office and one going to that office. Now these two offices aren't connected in this particular one by a logical permanent virtual connection. The idea of a permanent virtual connection, it seems to us like we have a circuit switch. So like a line that's just for us, it seems like that. And so that is a more, how would you say, we're not, it's like we're not sharing with anybody else. So it seems like we get our bandwidth out of that. So we call that a permanent virtual circuit. So the connection is established before we start sending data. So that's why I mean, it seems to us like we've got this connection which is permanent. It's not really. It's just before we set up that data, and it stays there until we stop. And we pay for the amount of bandwidth that was required. It's less expensive than some others because, you know, I mean, if we go away and not doing anything at night, we don't have to have that, you know, that could be gone. So asynchronous communication. So basically that means that, you know, we don't have to be going at the same, we don't have to be holding up a connection on both directions. We can sort of produce these virtual circuits as required. Okay, so we're going to have start and stop bits using packets, and with a fixed packet size. If we have a fixed packet size, mentioned that just before when we were talking about our other technology there. If you have a fixed packet size, it's easier to synchronize them, you know. So a packet is also, you should be familiar with that. Packet is level 3 technology. That means that it has a IP address at the start of your source IP address and your destination IP address. Packets are then wrapped to become frames. So the thing that's actually passing along the network is going to be your frames, but your frames, because they have packets in them, will be the same size, because that's the protocol that's being used here in asynchronous transfer mode. Now, why would it require more overhead? Because you got more packets. So if you have smaller packets, you're going to have more of them. And then each packet and each frame, it's got its headers, and they have to be processed. And so that's some extra overhead. But the efficiency there is because all the packets are the same size. And so it's kind of like easier to do that processing. And as I said, you sort of make up a virtual circuit, start bit, stop bit. And it's kind of like you had a phone line, but that's what we mean by a virtual circuit. It is considered packet switching. Packet switching is, you know, well, yeah, we have IP addresses on the packets. The packets can go independent of each other. So that's what it means. It means that you don't have to send, you don't have to hold the line up, and nothing else is on there but your message. And your message goes from start to end. That would be a circuit switch. That's like you talking on a phone. It doesn't have to be like that. That's like you talking on the phone 30 years ago, because even now you talking on the phone is going to be packets, because that's what they're going to do for efficiency, especially if you're using voice over IP with any of the, you guys do that, right? I mean, you talk on the phone with people, you know, on WhatsApp, you can voice and all of those, that's all done by packets. And so the packets is much more efficient. But you have a virtual circuit, so it seems to you like you've got a circuit, but that's just because we identify stop, start, and the end. We identify the fact that all of these packets belong together, even though they're going separate. And it's kind of reliable. Now we talk about quality of service, QoS. You should know about quality of service. It's the idea being that you will you'll get what you pay for. Basically, quality of service means that you can set up to have a higher bandwidth or a lower bandwidth, you know, a higher or lower reliability, depending on what you're prepared to pay. So that's what we mean by quality of service. It's important that you understand for quality of service that we have a differentiation, that things can be different, and based on what you'll pay for it. And yeah. All right, so that diagram's kind of small, but I hope that you can see here that we've got two sort of separated networks. Each of those separated networks has two different types of communication on them. One of them's got, this is ATM, which is going to have a high quality of service, so we pay more for that. Basically, the stuff here on the red is going to cost more than the stuff here in the blue. So that's what we mean by our quality of service. If we want this, we want to make sure that this ATM is coming across without dropping packets, without you know coming across quickly at a good bandwidth. So we're able to sort of get a faster better broadband through that, even though it's all going through this ATM switch. So the ATM switch is able to send that to our ATM router, and our router is splitting that out between the higher and the lower quality of service. We see that at the other end as well. So our red one there, that's going to be a more valuable, higher reliability, more bandwidth sort of service. And that's because it's required, right? We got voice over IP, we're talking to people, right? You want to hear it, as opposed to email. I mean, your email goes and maybe 5 minutes later, you're going to read it, right? And it's not going to, yeah. MPLS, that means that you're having multi-protocol. So multiple protocols can be used with that. Layer 3 protocols. And so you can have different types of payloads, different types of packets, different sizes of packets. So it's going to be able to sort of be a lot more flexible for you. And so ISPs are going to use that on their own network because they're providing service to lots of different types of customers. They're going to have lots of different types of service that they're going to provide. So they're going to use MPLS. And so, yes, so over a traditional circuit switch network. Now, I hope I've made the idea of what I mean by a circuit switch. A circuit switch is like when you take you make a phone call end to end, and it's as if you have that line and nobody else is using that line, that circuit switch, as opposed to packet switch, whereas you take your message and you break it into small bits and you send the bits out there and they go however, however the routers send them. And yeah, so it's a different sort of approach. And the packet switch is much more efficient, and therefore it makes it cheaper, and therefore everybody does it now, right? So all of our digital networks now work in that way. Okay, so the ISP, this could be a Rito. They have their network and they're able to provide services, VPN services, T1 lines, DSL, fiber lines, but they're not requiring that their customer have that fiber line, right? They're able to sort of just connect in with anybody because they're using those multiple protocols, which will allow the traffic from all these different kinds of things. So they're receiving sort of packets and frames of all different sizes, of all different formats, and they're able to sort of work with them. Okay, so the idea on wireless WANs. Wireless, we're thinking of wireless in a LAN situation, so our LAN situation, but what about for a WAN? Because remember, a WAN is for long distance. So what kind of non-wired service could we use for a great distance to connect two LANs together and have a big enough bandwidth so that would work? And I'm sure you can think of some straight away. One is you could use cellular network. Okay, so you could just connect over using the cellular. It's a digital network anyway, so you could use your 5 or 4 and or LTE to sort of provide that service. So that's when I was saying 5 or 4, we've got these generations here: 1G, 2G, 3G, 4G, and 5G. Now it does say that 5G doesn't exist, in which case I need to talk to Arito because they sold me 5G. So were they lying? I mean, sometimes on my phone it comes up and says that I got 5G on there. Not all the time. I noticed that. I know you must have it also. It's, my phone says 5G and then it says 4G. Sometimes it says 3G. Sometimes it says LTE. So I guess it depends on what cell towers around, what service I'm getting. But yeah, I notice some places around here I'm getting 5G. So this is a bit of old set of slides, I guess. That's 2019. It says 5G doesn't exist yet. Well, okay. Sorry, it's not that old of slides. It's only 2 years old. Anyway, so 3G, we've all had that for a while, and basically you're using your mobile phone, but you're surfing the internet, right? a little bit. Definitely with 4G, we're surfing the internet away. And with 5G, we're surfing the internet and we're doing it quite fast. So with 5G, I suppose we could use that as a WAN, right? To connect two big networks together, if you can afford it. So, I mean, it's supposed to be faster, and I guess it is. GSM. Now, it talks about these two competing voice technologies. I think it's referring here to CDMA. I haven't been to the United States for a long time using a mobile phone, but they used to use CDMA, and everybody else was using GSM. But you know, here we're using GSM, so you had to be careful if you had a phone from there, because you know maybe your GSM wouldn't work with it, or it wouldn't work if you brought it over here. But I think most of the phones now, they'll actually support both of these. Anyway, so yeah, but yeah, certainly we use GSM here. They use GSM in Australia. I think mostly in Europe and Asia, they use GSM. In the United States, they were using CDMA, but I think they may, don't know what they're doing with GSM, maybe. Okay, so the cell size, that's referring to, so it's a cell network, a cellular network. So the cell size is going to be the area that's going to be, the cell is, you have to think of it as sort of two-dimensional. So it's where you're going to get overlapping signals from multiple towers, so that you can pick up a signal, basically. Yeah, so depending on how you access that, you'll have different, and you've seen, so this is what we mean by the cells. Tries to draw them here as hexagons. But yeah, you see the various towers in that diagram. So the way those towers are set out, and that will, where they're put will depend on the topography as well, right? If you got hills and things like that. Yeah, they don't go forever, so you have to put them in a, like out in the desert, they have these mobile towers. All right, so, and that's what we mean by each of these is a cell. So if you're in your car and you're driving from here to here, up here, you're going to pass through different cells, and so you're going to have the technology which will allow the handoff, right? So you'll be connected to this tower, and then as you drive along, the other tower will come in, and there'll be some kind of a handover. And if that's smooth, and it is nowadays, you can have that conversation keep going without a break. And so that's kind of the magic of it, I suppose. So you got your central office, and we've talked about that, and then a mobile switching center, which is going to connect to all these towers. All of this stuff in between those two is probably going to be wired. But then the rest of our network out there is going to include those towers. Okay, so the mobile switching center, it's going to have high-speed access plus, is it called, 3G technology. You've seen LTE, long-term evolution, I'm sure. I see that's sort of faster than our standard 3G. All right, so that's enough on cell phones. I think this might be the last topic. Satellite technology. So we've had satellites up in the atmosphere. They're not in the atmosphere. They're above the atmosphere. They're supposed to be. I suppose for like 50 years or 60 years, since the 60s. And as it says, they're originally used for telephone and television signals. So people could watch TV and see stuff in the United States that was happening in Europe, and vice versa. So that's what they mean across the Atlantic Ocean. So people make phone calls from London to New York. Now they do have cable that goes under the oceans, but they also satellites was used a lot for TVs. And now the way those satellites work is this thing called a geosynchronous orbit. What it is, they put the satellite up at at a kind of very exact position. And so that's done by having a fairly exact speed. And so I think it's like about 160 miles. It's not that high, or 360 kilometers or something like that. But if you have the satellite going at the exact right speed, it'll stay in orbit at that particular height. And it stays above a particular point on the Earth. So it's like the satellite's always there. And so we have these, they're used for telecommunications, satellites like that. We've got a bunch of other satellites too, like our GPS satellites too, work that kind of way. But they're all in geosynchronous orbit, which means the satellite seems to always be in the same place in the sky above us, right there. And so so that means when you had your old TV that worked on satellite, you could just take your dish and point it in the right place, and you didn't have to move it around all the time. Just point in the right place. And if you go drive through the desert between here and Zubara, is that what you call it? The fort, Zubara Fort. There's a big telecommunications place out there, and they've got all the big dishes, and they're sort of picking up signals from, well, whatever, I'm not sure of it, but they're out there. And so, yeah, the satellite is able to, we can send a message to it, and we can receive a message back. So you can use it for a telephone call, or you could use it for as your WAN connection. And the satellite has transponders on it. So it's going to, we're going to send a message to it. The transponder is going to receive that message and send it back to another. Okay. Now, on your typical satellite, as it says, it would have 24 to 32 transponders. So that means it could communicate with 24 to 32 sort of transmitting stations on the Earth. Now, for TV, that would be different because it's a broadcast, right? So, they'd be receiving from 23 to 24 TV companies, but they could be broadcasting to whoever can pick up the signal. And so they use frequencies, and you notice that with your satellite too. You have to tune it into the right frequency to get this. Now, we used to have some satellite telephones that you could buy. There was one called Thurea. I don't know if you guys ever heard of that one. But yeah, back in the early 2000s, late 1990s, you could buy from, well, I was in UAE then. You could buy from Etisalat. You could buy a Thurea handset. And the thing about it is you could just walk around in the desert anywhere, all the way through anywhere, through Saudi Arabia, where there's no cell phones, and you can make phone calls because your phone is directly connecting to the Thurea satellite. But as you see here, that's not what this is. What this is we're having those special stations like the one up at Zubara, and it's sending messages up, and then they're being sent on to another one. So that would be working for your WAN type technology. All right, so they've got a bunch of different bands at different gigahertz. Some of these bands, I did see some of these show up. You might have to look at a couple of those, certainly C-band. Might show up in your exam. So just beware that that we can split out by the different frequencies. So what this means is we're going to send different signals on each of these. So you could send from the same place a bunch of different signals just at different frequencies, and so you're getting a lot of bandwidth out of that by splitting down the frequencies. Each band, yeah, okay. Yeah, I think you could do internet services through satellites. I think that's looked at as a good thing to do in sort of countries that don't have a lot of infrastructure, don't have fiber. Looking at sort of doing that is, just have satellite provide your mobile phones as well as your internet. But typically asymmetrical, so that means that your upload speeds are going to be different to your download speeds. So with internet, you'd probably be using it for sort of providing you with services, maybe watching Netflix or something like that. So you'd want faster download than upload. You're not uploading much unless you're doing some kind of business, you wouldn't need big upload speeds. So download speeds are going to be higher than your upload speeds typically. Now, you do need, if you're using internet, you do need some upload, right? When you do a like on Facebook, that's going to be, but it's not much data, right? Unless you're sort of, if you're making movies and putting them up there every day, well, then you'll need a little bit more. Okay, so that's the end of that topic. I hope that's sort of okay for you. The summary that I've got here is actually, when I looked at it, it's not actually a summary of this topic. So this is, but it's good to look at. It's basically a summary of a previous topic when we were talking about security. So don't be confused by this summary. Read this summary along with the notes that go on security. So about proxy servers, what we can do with the proxy servers, we're standing aside from our network kind of thing, right? So we can keep people outside, away from knowing our IP addresses and things like that. It makes it a little bit safer. Acl Access List. So that the router will be able to exclude certain entities and include others that access to our content based on a list of those that are allowed and those that aren't not. The idea of a firewall. So a firewall could be a physical device that would be separating us from our proxy server, because we put our proxy server in a place that we call a DMZ, a demilitarized zone. And then another firewall to separate that from the outside world. And intrusion detection. Now there's two things that kind of sound the same. Again, this is all about this. So I'm just going to go through this because I've got the slides, but the intrusion detection system and something similar to that was a intrusion prevention system. But basically we're having software on our devices that are able to see if somebody's trying to attack us. That would be an intrusion detection system that's sort of looking for changes that are not normal traffic. And whereas an intrusion prevention system is a little bit more proactive. It'll actually do things to stop the attack, not just to say, hey, I'm under attack. So IDS is about monitoring. IPS is about actually stopping it, stopping intrusions, cutting them off. Spanning tree protocol. This is to do with routers. So routers have different protocols so how they actually work so that the router connects to other devices, calculating the path. And so that can be used as part of our security. We can make sure that any ports that are not being used are blocked so that unwanted connections are not made to our networks. These three things, that actually does show up in the exam: authentication, authorization, and accounting. So we call that AAA, AAA. Hopefully you're sort of familiar with that. So authentication, are you who you say you are? And there's like 5 things that they might be asked, something something you are, you remember those? Those are in your notes. Geofencing, GPS and RFID data as part of your authentication. Are you in the right place? Do you have the right device? These type of things. Logs that can then be analyzed with some kind of auditing software, could include some kind of statistical analysis on it to sort of see if things are sort of unusual. And then we can sort of see if some kind of attacks are happening. Okay, so our NAC set of rules, network policies. So we can have as a network administrator, which you guys may aspire to be, I suppose. One of the things that you'd have to do is sort of set up some rules, protocols, policies that you would have there. Cabarrus. Cross-platform, so I guess that means that it's working on Linux. Single sign-on. Single sign-on, what that means is that you sign on at one interface, and you're allowed to use multiple systems with that single sign-on. So for us here at the college, we kind of have something like that. We sign in to the college intranet, and then we can use PeopleSoft and we can use D2L with those same credential login. Remote authentication dial-in user service, Radius, which is, as it says there, a AAA service. So if it's remote authentication, that would be allowing you to sort of get in and maybe make a VPN connection to your network. What's that one? Terminal Access Controller Access Control System Plus. Woo. Well, I can tell you that's not coming up in the exam. So WEP, on the other hand, might be. So yeah, WEP, authentication on a Wi-Fi. And so when you look at your authentication for your Wi-Fi, you'll find that in your notes that you saw a progression from the earliest sort of weak authentication to more to better authentication. So you might want to look at that. And TKIP is about that, right? TKIP was a TKIP was to fill in the weakness of your WPA or WEP. And so this is that evolution of better security for Wi-Fi, going from WEP to TKIP to CCMP, WPA2. These are all about newer security for that. And WPA added security, and that's it. So that's the revision of last time. Woot! As far as I know,